Yes.
Doing some notes? Okay. We ready? Gentlemen. All right. Steph, give me the notes. Okay. So, first off, I want to say some good news about this question. So if you guys remember, this question is replacing the types of solid question from last year. So the ionic solids, metallic solids, etc., etc. That one I feel was a really big question because it varied very much in what they could ask, because there was lots of different properties, and also depending on the solid you were dealing with, you would have slightly different answers. The nice thing about periodic table trends is that a lot of the justifications will overlap. So even though we're looking at 3 different things for the trends of the periodic table, the way you justify it is more or less the same. So I quite like how that is. So first thing, let's talk about the periodic table. What we are looking at is patterns in that periodic table and trying to explain them. There's going to be 3 patterns that they're going to be looking at. So we're looking at patterns in the periodic table. Let's get that to focus. Okay, so the first thing we're going to be thinking about as a pattern is going to be electron negativity, which we briefly talked about last year. I'll talk about these in more detail when we get to each one. That way you don't have to backtrack too much. The second one you're going to hear about is going to be ionization energy. And then the third one they're going to be talking about is going to be atomic radius or ionic radius. So that's basically how big the atom is. So the nice thing to think about with this is that when it comes to the justification, like I said, regardless of which one they give you, is more or less pulling on similar principles. So that kind of reduces the load when it comes to learning. So when you're trying to justify these trends, there are 2 main things that you'll probably be talking about. The first thing you're going to be talking about is the size of the nucleus. So basically how many protons are in that nucleus, because the more protons there are, the more of a pull it's going to have on the electrons. So we're thinking about the size of the nucleus because that's going to affect how much positive charge we have in that core, and that's going to then influence how strong we can pull those electrons outside of us. So that's the first thing you're going to be talking about. The second thing you're often going to be talking about is going to be the distance the valence shells are from the nucleus. So most of these properties, in fact I should say all these properties, are going to be dependent on the valence electrons, which is our outermost electrons. Outermost electrons are going to be influenced by how far they are away from that nucleus, for 1, just the distance between those 2, but 2, something called shielding. So something to keep in mind is if I have like my positively charged nucleus, we have lots of different shells of electrons. I know I'm doing it as kind of orbitals. Now, let's say I'm thinking about these electrons here that are in my valence shell. Then there's the electrons that are also existing in the shells below it. Now, something to keep in mind is that these shells here have what we call a shielding effect, and because they're negatively charged, they're going to cancel out some of the positive charge pull that the nucleus has. So in each one of the examples we're thinking about, electronegativity, ionization energy, and atomic radius, both of those things are going to be influenced by the size of the nucleus and also how far those valence electrons are. Are we okay with that so far? All right, cool. I'll leave that up for a second just in case people are still writing. Just checking my notes, make sure I don't forget something. And I want to see if I can find the notes the other day. If I like that picture, which it actually might still be my bad. Did I grab all the papers I wanted to bring over? No, it's not that smart today. That's okay. I have to pull it off the board. Okay, move it. Okay, so the first thing we're going to be thinking about is our electron negativities. So that's why I printed out these guys for you, so you can write along with me. I find it's really helpful to annotate on the diagram so that way we know what we're talking about. So the first thing when we're talking about electron negativity, and hopefully this is a refresher from last year, we're talking about that attractive force between the nucleus and the valence electrons. So the more electron negative something is, the stronger its attraction, those valence electrons to that nucleus. The most electron negative element we have is fluorine. Fluorine, again, actually we'll explain why that is with the new notes. Are we okay with that so far as a definition? Electronegativity. Okay, so there are two factors that are going to be affecting electronegativity. The first one is going to be size of the atom. So if you guys notice when we're looking at it, when we're going down the periodic table, what do you see happening with the electronegativities? It's generally decreasing. So as we go down the periodic table, we see a decrease in electronegativity, and we need to explain why. So the thing that you have to keep in mind with this case is that as we are going down, we are actually adding more shells. So the atoms are getting bigger. And since we're adding more shells, we're going to have more distance from the valence electron to the nucleus and more shielding effect. So there's going to be, since those two factors are coming together, the electronegativity is going to go down. So this is the result of more shells being added. So we're going to have a greater distance. Means we have greater distance, and the other thing is going to be we have more shielding. So that's going to influence our electronegativity. Just to kind of further prove that point, when we look at this over here from the other day, you see again how you're going down. You have a 2s, then 3s, then 4s, then 5s. So again, you're building your shells larger and larger. So you have all the stuff before it now encompassing it. That's going to start shielding the nucleus, so the nucleus cannot pull as strongly to that valence electron. So that's how we see going down. Same thing in here, 3D, 4D, 5D, 2p, 3p, 4p, etc., etc. So everything, when we're talking about our valence electrons, are going to be a little bit further and a little bit more shielded. So that's the first thing. The second thing is a little bit more challenging to understand, but that's okay. And that's the trend going this way. So when we go this way, we notice that we have our electronegativity is increasing. And the moment we hit the end of the row, we go back here and you see how it suddenly drops back down again. And then it increases and then drops back down. And then increases and then drop back down. So we need to, again, understand why that is occurring. So what we can state as a trend is as we're going from the left to the right across my period, we notice that the electronegativity is increasing until we start a new row. So, like I said, this one is going to get a little bit more complicated to understand, but that's okay. So something we have to keep in mind is that yes, we are adding more electrons. We are also adding more protons. And as we said, okay. So as we're looking at this, remember how I said Remember how I said the size of the nucleus is an important factor with how strong the pull is to the valence electrons. So as we're going across the period, we're getting more and more protons in that nucleus. So that's going to create a stronger pull. Now you might be adding, go, Miss Scarlett, but we're adding more electrons as well. Shouldn't that cancel out? And the thing you have to remember is that yes, we are adding more electrons, but we are adding them to the same subshell. So we're not actually changing that component when it comes to shielding. So they're going to be added. So see if I'm looking at this guy over here with the 2p, yes, I'm adding more electrons, but they're being added to the same shell. So I'm not actually increasing any of the distance from those valence electrons to the nucleus, and I'm also not increasing any shielding effect. So that's why as we're going this way, we start seeing the electron negativity increase. The moment I have that electron negativity drop is when you start a new row, and when you start a new row, you're starting a new shell. So we've gone from 2p to 3s. So we start a new shell. Now everything below it is now shielding the nucleus. And so that's why it's resetting. So that's the thing that's important here. So in this case, we're going from right to left, the period and the row. So you are adding protons. Spelling nucleus, right? Because my brain's fried. Adding protons to the nucleus. So you have greater nuclear pull. And so even though we're adding more electrons, the electrons are being added to the same shell, so we don't have a change in shielding. Amount of shielding or distance. This first one's always the most notes, and then basically use the same justification for everybody. All right, questions, concerns, or comments at that point? Can I move it? Yeah. Good. Oh, I still see some pens moving. All right, then I'll talk about ionization energy. Ionization energy has a couple of little exceptions, which I'll point out to you. Yep. The electronegativity. I'm just lazy. I have all these random shorthands. Do not do that on the assessment. I'll know what you mean, but not the examiner. All right, so the good news is a lot of things will now parallel with your justification. So this is what I'm saying that makes it nicer to structure and bonding is that there's less variation in how you have to answer, which is kind of nice. Yeah. All right, move it. So next thing we're talking about is electron negativity. So electron negativity is talking about how much, sorry, not electron negativity, ionization energy is talking about how much energy you need to put in order to remove that valence electron. This is just some extra stuff from 1 mole of element in the gas state. So the amount of energy needed to remove 1 valence electron from 1 mole of the element. Something that I find a lot of people get kind of confused on when I see on the exam is they ask you to write the equation for ionization energy for various elements, and they get really thrown off by things like fluorine because they're like, oh, but it forms a negative ion. everything we are assuming is losing one electron. So when you guys are writing these equations, just be mindful, like if I was doing sodium, I would have sodium as a gas, and then it'd be forming sodium, the ion, gas, plus one electron. All of the equations are going to be the same for the ionization energy because we're always talking about removing one electron. So if I have fluorine, for example, I would have fluorine, gas, fluorine plus gas, and one electron. So it's going to look a little weird because you guys are used to adding electrons to fluorine. That looks bizarre, doesn't it? Yeah. But that's what they're talking about when they ask you to do equations for ionization energy. So all you're doing is taking the element, putting it in the gas form, removing an electron, putting it as a positive one charge. Are you okay with that so far? All right, cool. This obviously follows the same trends as the electron negativity because it makes sense because we're talking about, for electron negativity, the attraction between the valence electrons and the nucleus. And if something is more attracted, it's going to require more energy to remove it. So we'll follow the same trend. Going down, you see a decrease in the electron negativity. Going across, you'll see an increase in the electron negativity, in the ionization energy. They go parallel, which makes sense. Because if I'm talking about how attracted they are, we're going to be talking about also how much energy is required. Are we okay with that so far? Yes, no? Okay. Now, there is some exceptions to the rules, and that's why I included this table down here. What you'll notice is that there's generally a trend of, yes, as we're going across the row, it is increasing, but you see there's little dips. So you see beryllium and boron has a dip. Magnesium and aluminium have a dip. And then you see nitrogen and, I'm going to change colors actually. Nitrogen and oxygen have a dip, and phosphorus and sulfur have a dip. All right? And it follows when you guys are looking at the periodic table as well. So here's beryllium. So we see lithium to beryllium, it does increase from 520 to 899, and then it suddenly drops to 800 with boron, but then it increases back to 1086 for carbon. So we're basically trying to understand, why does this happen? And also, why does this dip happen as well? Because you would expect it to have a consistent trend. The reason has to do with the electron arrangements for those elements. So when we're looking at beryllium and boron and magnesium and aluminium, let me write their electron configurations to show you why there's that dip there. So beryllium is 1s2, 2s2, whereas boron is 1s2, 2s2, 3p1. And then when we're looking at magnesium and aluminium, it is
house that is going today is cool. Participants, please meet at the beginning of break 1. We have your lunch ready for you. Thank you, and see you soon.
all right. So the thing that we need to be mindful of, so we have basically the exact same setup. The only thing that's different is that we have a 2p1. This is actually quite easy to remove because it's a new subshell. And this, when you're talking about that, is paired. So paired electrons are obviously going to be a little bit easier to kind of keep together. So that's why that's a little dip. We're just starting a new shell. All right. The next one we're looking at is the the nitrogen and the oxygen. So nitrogen has 1s2, 2s2, 2p3. Oxygen has 1, just writing it down. And then same thing with the phosphorus. Just trying to write it fast and mindful of our time. So these little blips are the result of just chance and how they're filling their subshells. Okay, so again, what we notice here, that's a 3, that's a 4, that's a 3, that's a 4. So what has happened, if you guys remember, that when we are talking about how we fill our subshells, we always fill one electron into each subshell first. Okay? So that's looking at nitrogen and phosphorus. 1 electron first. And then once we get to 4, you're starting to fill 2. Right? Now, the problem is, or what happens, I should say, is that because we now have 2 electrons there, those are both negatively charges, and we know that like charges repel. So that's why it drops again when you get to oxygen and sulfur, because now you have 2 in that first shell, and so it's easy to rip it off because it's already got like charges repelling. So that's why that one is also a weird little dip. But everyone else follows that trend. All right? So fluorine, when you think about it, it only needs 1 more valence electron to fill its outer shell, so it's going to hold on to its valence electrons really, really tightly because it's more stable if it just gains 1 more. So that's why it's such a high electron negativity, and it's also why it has a high ionization energy. The other thing to keep in mind is that fluorine is also the smallest of those atoms in that whole list, and so that makes it, again, a lot easier for that proton to hold on to its valence electrons. Something else to keep in mind as a note is that every additional electron we remove, it's going to require more and more ionization energy. The reason why is because now I have a disbalance in my charge. I have more positive charge than negative charge, and that's going to be a stronger attraction to the remaining valence electrons. So if I try to take a second one off or a third one off, it's going to progressively get more and more difficult. Are we okay with that? All right. Last thing, I'm just mindful of our time, is going to be atomic radii. So we're talking about the size of our atoms, and again, ties back to the same reasoning. So I have my positive nucleus, and it's pulling on the valence electrons. If it can pull on those valence electrons really, really well and pull it tight, it's going to have a smaller atom. If it doesn't have that strong attraction, then it's going to not hold it as well, and it's going to be a slightly bigger atom. So we see the same trends going down. As I go down the periodic table, I get bigger and bigger atoms because we're getting increased shells. So that is 2 reasons. First off, we have more shells. Second off, we have more shielding. So more shells, more shielding. I'm just trying to find a color I didn't use yet. More shells and more shielding effect. So these are getting larger. As we're going to the right, your atomic radii is getting smaller because, again, same reason that we've talked about before. We are, yes, adding more electrons, but we're also having more protons, and that's going to have a stronger nuclear pull. It's getting added to the same shell, so it's getting it smaller and smaller and smaller. So that's why these atoms are getting smaller that size. So you see what I'm saying? The justification is the same. The other thing they often ask with this is about the ions forming and how that's going to influence the size of the ion versus the original atom. So in this case here, when I'm looking at my positive ions that are forming, my positive ions are going to be smaller than the atoms. And that's because of 2 things. First reason is that we have lost a shell, because when you're losing electrons, you're taking it from the shell that's outside. So let's say if I'm taking it from lithium, I've had a 2s shell, and now I'm going down to a 1s, for example. Or if I have this one here, I'm going from a 3s down to a 2p. So I'm literally losing a shell. It's going to make it smaller. So when we're talking about positive ions, they're losing shells. The other thing to keep in mind is since we're losing electrons, I now have more positive charge than negative charge, so the remaining electrons are going to be pulled much, much tighter together. So everyone gets pulled in a little bit more. Obviously, the more that I have the more charges I lose, the stronger that pull is going to be. So that's why these guys are super tiny ions compared to their atoms. The negative ions have the opposite effect. It's important to remember that in this case, you are not saying that you are adding shells. When we are adding our electrons, we are still in that same subshell. So it's not bigger because you're adding shells. So be careful with that. It's something that you do write in the positive, but you don't write in the negatives. The other thing to keep in mind is the reason why this is now bigger than its original atom is because now you have a disbalance in charge. You have more negative charge than positive. So what that means is that the remaining protons that are there, the protons that are still there, hasn't changed, the protons that are in the nucleus have to do more work holding onto all the electrons. So when you divide up that positive charge, it doesn't have that same pull. So they pull on it less strong, so it makes it a bigger atom, bigger ion. That's gonna make it bigger. All right. That's everything. Let me point out some things because I know that's the last minute. Cool. We've done that. We've done that. Just be mindful, Mahi choice wise, or what you want to do following up. You can go back to the SciPad pages. You can do the no brain too small collated questions. I've also put a CPR quiz on there. I only recommend doing the CPR quiz after you've done some practice questions. I haven't made a copy for each person because not everyone's doing organic. So if you do it, attach it onto the assignment post so I know what I'm doing. Okay? And flick me an email so I know. All right, that's that.